All right, so let's start. Jonathan, can you maybe turn on your camera so that we can see you? All right, great. Okay, so welcome everyone to the Livia seminar. So today we have a presentation by Jonathan de Matos, who's a PhD candidate at Livia, supervised by Alessandro. And today his talk will be on large margin representation learning. So Jonathan, the floor is yours.
Okay, thank you. So, as Professor Christian already introduced me, I'm working.
So Jonathan, I think the sound is not very loud for us. Can you maybe increase the microphone volume?
Now it's okay?
It's better.
Yeah. Maybe.
There's a bit of noise. There's a bit of noise when you talk. So maybe, I don't know if you can remove your earphones or...
Okay. Maybe
now it's good. Now it's good.
Good. Okay.
Yes.
Okay. Thank you. So I'm a student from Professor. I'm supervised by Professor Alessandro Lameira. We are part of a program of international collaboration. So I'm also oriented by Professor Alceu de Souza Brito Jr. That's also here in the call. So I'm going to present my a work that we are developing the recent in the last months. So I'll start the presentation. So the title of our work is large margin representation learning. So I'll do a little introduction about the topic, about what we are trying to develop. I'll talk about the research problem that we faced that motivated our proposal. I will explain all the proposal, the experiments, and results that we managed to achieve. Then go to a conclusion and our contributions from our proposal. So as an introduction, we are working with basically with textures. So textures are patterns that are found in a lot of problems, in a lot of image problems. They even in problems like object recognition and everything, we have textures, but they are of course grouped, and this is what CNNs do very well. But in the past, we have a lot of other solutions involving textures. So people use before the CNNs, people used a lot the handcrafted feature extractors like GLCM, LBP, SIFT, and a lot of other proposals. These handcrafted feature extractors, they are easy to be trained to extract features from small data sets and train monolithic classifiers. So this is an advantage for small data sets with textures. But when we started to go towards the deep learning architectures, we faced another reality. So in the deep learning gets popular with the use of with the ImageNet dataset that is very big. So with a small dataset, deep learning is kind of problematic because we have a lot of parameters to train and everything. So there are some proposals that use CNNs for texture. We have, for example, a proposal from 2015 from Simpoy that uses FV CNN that is basically using a CNN as a feature extractor, something like that. And we have also another proposal in 2016 from a student from Ireland he proposed the texture CNNs. That is basically a CNN, a complete CNN, but with global average pooling after that he calls energy layer at the end of the the convolutional layers. So we merged some of these ideas and also joined these ideas with the idea of the deep metric learning. So how do we use that? We proposed training. The point is that training CNNs with small data sets is difficult because the amount of parameters, but CNNs as feature extractors, like the work of Simpoy and other works, they work kind of well. I myself worked with, for example, ResNet and Inception as feature extractor for histopathological images, and they work very well. And we just use them as they are trained, and we use the last layers. Maybe some people use it at the fully convolutional layers. Some people use at the end of the convolutional layers. And they are static, but they produce very huge feature vectors that are used to train some, for example, nearest neighbors classifiers, or SVMs, or decision trees, other monolithic classifiers to recognize the textures and other simpler stuff. Textures, they don't need very deep networks, because textures are identified in the first layers of the network, and as we go deeper in these networks, we tend to start to go more a domain-specific task, and start to recognize shape and spatial characteristics. So another problem using CNNs as feature extractors and using, for example, the DEF-C layers is that the input image should have the same size of the output of the input image that the network was trained. So we have to rescale the image, and we don't have this flexibility. So the objective of our proposal is to use this idea of CNNs and as feature extractors, or better, use only the convolutional layers as feature extractors. And so based on fully convolutional, it will be like a fully convolutional network, and use these networks to generate a representation that is more suitable to a specific classifier. So in this case, we are working with a large margin classifier for supervised learning. So our method, we developed a representation learning method that combines the convolutional layers, a sequence of convolutional layers, and a global average pooling at the end of them. So we don't have, we are not anchored, we are not fixed at the input size. So we can use any input size to our network, for example, and use a large margin classifier to give us information to train these convolutional layers. So we are performing deep metric learning on the convolutional layers using information from a large margin classifier. So this is to perform this. When you talk about deep metric learning, the major focus is on the loss functions. So we created a loss function that has three parts. This loss function gives us the error value. It's not really an error, it's a distance, as we talked, to the training algorithm, to the optimizer, to train the weights of the convolutional layers. So the three parts are for loss function is a distance vector at value, that is the distance from the support vectors to their anchors. I'll explain what are their anchors that we are talking here. Another part is the distance from misclassified instances to their anchors too, and the distance between correct classified instances. So what are the anchors? Here we have a representation. It's like all these points. The circles are from one class. The X are from the other class. We are showing here a representation with like a 2D dimension representation, the representation of space. So here is like we provide an image to our function, to our network, to our fully convolutional network. It provided us with two features, with a feature vector, two attributes. And we use here with like representation here, our representation here is showing two-dimensional. So we have here the two classes. One is the one space of one class is the yellow part. The other is the blue part. The axes are from one class. The circles are from another class. The big axes are support vectors, and the big circles are support vectors. So in the first image here, we have the example of our first calculation of our loss function. So in red here, we have the anchors. In this case, these 3 points here, these 3 instances, they are anchors for this support vector. So we measure the distance from one support vector to 3 anchors. In this case, 2. We sum all these distance, and of course, the optimizer tries to minimize this value. The same occurs to the other class. So we're trying to move these support vectors in this direction. This one in this direction. So we are moving them on the right direction, and the other class works the same. We only use as anchors for the support vectors a number we can determine. In this case, we are using 3 anchors. These anchors here, they are correct classified instance from the same class as the support vector. In this image in the middle here, we have an example of the second part of our loss function. So here, we have the misclassified instances here. We have another misclassified instance here, here, and their anchor are the support vectors from the same class. So this support vector here, now that is marked with red, in this part of the loss function, it is working as an anchor for these 3 instances here. The same occurs here, the same occurs here. So we are also moving here the instances, when we minimize this distance that the optimizer will try to do, we're moving the wrong misclassified instance to the right place. In the third part of the loss function, we have, for example, here we have an anchor. Here is this circle here in red is an anchor to these 2 instances. In this case, we are not trying to move them closer. We will maximize this distance in order to push distance from opposite classes to opposite directions, to their correct position. We will talk a little bit more about the importance of these parts a little bit later. So to define some parts, some things here, we take a training set named as X that is composed by a matrix of images, and their outputs. With this information here, with these images from the training data set, from the training set, we create a square difference matrix that is calculated here, that is calculated based on the output of our fully convolutional layers. So we provide the image to our fully convolutional layers. They produce a vector with a feature vector that, in this case, for example, in the previous example of our representational space, it was a vector, for example, with 2 attributes for 2 instances. We calculated distance. Basically, in this step here, we calculate the square difference between all the instances. So this matrix P here will have n by n dimension. Based on this matrix, we use it in 2 parts to calculate an Euclidean distance matrix B and a kernel matrix K. That is basically, this is an RBF kernel, and we do this in order to use the resources from the GPU. So we all the images that we present to this FCNN, they return their feature vectors that are in the GPU. So we calculate maybe it's one of the most costly part of the, for example, an SVM. So we use the GPU to calculate this part. So it's kind of efficient. So, and we reuse the distance here that we are going to use this matrix to calculate our anchors. So this is the FCN that we are using. This is the function that does this transformation here. In this example, it's we use this in all of our results that we're showing in the future. So it's basically a very simple FCN with a global average pooling at the end. So with a configurable output feature vector. So if you take a look here, we see that after the global average pooling, we don't have any more the information about the weight and height of the image, and we have only the mean of the entire image, the activation map mean for each combination of convolutional layers. So how do we calculate the loss function? How do we use all this information to calculate the loss function? We create a matrix A. So in this case, here it's a vector from a matrix A that is basically all the support vectors that we have in our network. So in this case, we take the distance matrix. We take all our support vectors from a set S, that is a set of support vectors, and for each of it, we do an arg sort. So we get the closest instance to this support vector, filling these conditions here. So in this case, we have all in this matrix A, we have a lot of vectors that have the indexes to all the closest correct classified instances to all the support vectors. In this case here, the second part of our loss function, we have the misclassified the indexes to all the anchors that are closest to this argsort function here to our misclassified instance. So in this we have all the pointers to or the anchors from the misclassified instances. Here we calculate the same. So we have the G is a matrix with each line. It's a vector with indexes to all the closest anchors that are correct classified instances from the opposite class. So we get it here by this information here. So our loss function is calculated like this. An important factor here is that we take only this part here, this T is, I haven't showed it, but it's basically all the static values of the images that the training set images. So here we have really anchors. They are static values. The only values here that have gradients that will influence the training in the loss function, that the loss function will provide the value that the optimizer will try to reduce with the loss function, are the images from the are the support vectors. Here we have a parameter here that is called as the close. That is the amount of closest anchors. This is work kind of a weight in our proposal. Here is the same. So these two functions are very close. And this one is the inverse, because we are trying to maximize the distance between opposite class instances. And if you take a look here, we have here the part of the gradient, the part that provides gradients in the loss function for the optimizer, and here too. So these are the images that we are trying to provide information for the optimizer to reduce the distance. And here, these T are all static values. So here it's the overall of our proposal. So we take the input training set, we provide them to an FCN. It returns a vector matrix with all the instances, the feature vector of all the instances. So it's n by f. It's already reduced, so it's not that huge in the memory. We calculate p. That p is used in these two parts here to calculate the kernel and the distance matrix. This part here, this part 2, it's as though as the part 1 here, it's all calculated in GPU, so it's kind of efficient with this kind of calculation. And here we have train SVM. Train SVM is basically we use the our kernel or RBF kernel, and we provide them to the optimizer, for example, the SMO, and we create the Lagrangian multipliers with all the information, and we extract the support vectors from it. So these support vectors are used to calculate the matrices A, M, and G, that are matrices that are used in our loss. And we, in the back propagation step, so this is all forward propagation, and this one is used in the back propagation step with the loss functions. So here we update our FCN again. And this process here repeats at every epoch. So we have another kernel, another SVM at each epoch. So we retrain the SVM at each epoch. If we take a look here, as we use this large margin classifier, we only have 2 classes. It's a binary proposal. So to transform it in a multi-class proposal, we propose this one versus all scheme. That what we do here, we train n with n classes sets of FCNs and SVMs. So at the end of each process here, we will have like a feature extractor in this FCN here that is able to differentiate between one instances from one class and the other one, and the rest of the class. With this, we can be a little more focused on the characteristics of a single class, and this, as I will show, presented us with good results in the imbalanced scenarios. So after training all these sets here, this FCN and SVM sets here, what we do, we train another large margin classifier that is trained with the concatenation of all the outputs from these FCNs. So here we train another class at the end of this, for example, 10 epochs here, 10 epochs here, 10 epochs here, 10 epochs here. We have another classifier trained in the end that will, of course, this classifier, it's a large margin classifier too. So it's an SVM multi-class. So it also uses like one versus all or one versus one, with one versus one here. because it's a small problem. So in this case, we have now multi-class proposal. How do we evaluate our proposal? So we used 5 small data sets. We created one very simple synthetic data set that was based on Gaussian images. So we take an space of some height and width, and we generated each pixel with based on a Gaussian distribution. And we create 2 classes from like 2 different means and standard deviations. And we also, in this image, we created a random striped pattern oriented in positive angles for one class and negative angles for another class. So it's a very simple data set. It kind of doesn't make sense, but we use this to see how our proposal is working. And we also use the Salzburg texture image dataset. This is a 32 classes texture dataset. We used only 2 classes from this dataset. We use the 2 major classes, that is miscellaneous and fabric. And so in this case, it has like 1,700 images. We also used here the break his dataset. That is a dataset from breast cancer images. We use the ICR back dataset that is also a breast cancer dataset. This one here, break his, it can be evaluated as a binary dataset or a 8-class dataset. In a binary format, it differentiates between benign and malignant tumors. The back dataset differentiates between 4 types of diagnosis. So no cancer, benign cancer, ductal carcinoma, and invasive ductal carcinoma breast cancers. And we used another dataset that is CRC. It's a dataset of colorectal images. In this case, this dataset is also 8-class dataset. It has some kind of a binary proposal that even the researchers that proposed this dataset presented. It's a very simple binary dataset. It's very easy to recognize, as you see in the results. But in the 8th class, we have better results even as the baseline of the dataset. As metrics to evaluate our model, we used accuracy, balanced accuracy, because we had some imbalanced data sets. So break his and the Salzburg they are imbalanced. We used another different evaluation metric here, that is the feature complexity. It's a library for complexity for features. So it's a very interesting library that uses like geometrical information. So in our case, it's very useful because all our proposal is based on distances. So it's a very good way to evaluate our features. And we also use the UMATs. I will not present the UMATs results here because they take a lot of space. So through this one here, I will not present them. As comparison, we did not compare with like huge CNNs or standard models. We used CNN for texture. So we take the same FCN that we used in our proposal and added fully convolutional layers at the end of the FCN. So we create the CNN. That is the basic idea of the work from 2018, 716 from the student from Ireland that I cannot pronounce the name. So we have here we trained these CNNs with hinge and BCA loss. We also compared with GLCM and PFS and LBP, that these 3 here, they are handcrafted feature structures. Here, we show our comparison between our FCN-SV, or our proposal, We have here the results from CNN with hinge loss and BCE loss. They did not present very different behavior between them. So here we have for the data set back. So the training data set presented a very huge difference between the training behavior. And as you can see here, we only trained our model for 15 epochs. And the CNN, they were training for 100 epochs. And even we have here that in the first epoch, we already have very good results with our proposal. And this also can be seen in the validation dataset and in the test dataset. Of course, it's kind of make no sense to use the plotted graph of a test dataset, but we put here just for us to take an idea here. These values here from accuracy, they are balanced accuracy, and they are taken from the best validation value. So here, when we achieve the validation peak here, we take the best training accuracy and the best test accuracy. So here we can see that we have an advantage. Here we were able to obtain a good value here with only 15 epochs. And I'll talk a little bit later about the time that we take to calculate an epoch, but we have some advantages too. So we take less epochs, and our epochs are smaller, are less costly. Here for a break-his data set, so we have here for the training data set, validation data set, and for the test data set, we have an improvement here, we have improvement here, and of course, we have in the CNNs, we have the good values here at almost at 90. So it's we converge faster. In the case for the CRC dataset, it's a little bit strange because it's so easy in the binary configuration that even the FCN, because of our FCN is kind of have a lot of channels. And the SVM classifier was able to obtain good results even the beginning of before training. So it's so a random network here would perform well because the data is so easy. And here for the Gaussian images, we have also advantages for our proposal with a very fast convergence here in the first epochs. Here is for the Salzburg data set. We also have very fast convergence with better values here, of course, taken from the best validation value. So in this case, analyzing our proposal with the equivalent CNN proposal, we could note some kind of advantage for our proposal, and we have also the cost advantage that we show later. So the complexity metrics that we use, we are able to evaluate mainly this kind of values here, the N1 and N2. This value here, N1, it evaluates how well the margins are defined. So in this case, we can see that in the first step, because we have an improvement from separation, we can define better our margins in the first epochs. And with N2, N2 is measures it's based on the Euclidean distance from instances from the same class and instances from opposite class. So in the first steps of our training, we were already able to separate better the data. We have here these two, just the accuracy, just for us to take a look here that what is representing here. So we have improvement here in the training accuracy. We have also here this F1 and F2 measures. They are measures from a single feature. So they take like the better value of a single feature from the feature vector. So if the data set is, in this case, F1, the biggest the value, the easiest solve the problem. So we have here, with this information closest to 1, we have the meaning that we have one single feature that we're able to differentiate all the data set. So we have a single feature. We could reduce the data to a single feature that would represent better our data set and allow us to do a better separation. F2 evaluates how interleaved the classes are by feature. So the smaller the value, the less interleaved the classes are, and we have at least one feature that could separate the classes. So we have also good values here. It increases with the training. Basically, in this case, this occurs because we use the Euclidean distance. So in our training, all the values are affected in the optimization step. And here we have another valuable information that is the support vectors. We see here in the first epoch that we have a drastic reduction of the support vectors. So this is very important for training, that because it allows our training. It shows that we are separating better the data, and also they they make our training less costly. Here are the results comparing I use here the old name that we're using. It's the FCNSV, our proposal, and the handcrafted feature extractor. So we have here compared with LP, PFS, and GLCM. If you take a look here at the test data set, it's most important. We have advantage in all the situations here to our proposal, and it's very stable. If we take a look, and the other data sets, the other feature extractors, for example, LBP, PFS, and GLCM, each one has an advantage in one data set. It occurs in some cases here. If you take a look, for example, here, in this case, LBP, it's better than PFS. It's a little bit, but it's better than PFS on Salzburg. But here, it's better than PFS here. But here, PFS is better. So this shows that our proposal can be, our simple proposal can present, can adapt our filters to each of the dataset needs. In the multi-class results here, we also have good results. For the back data set, we have, for example, in the test data set, we have achieved the better results. For the break-his, we also have achieved better results than the other proposals. Here, with the GLCM, LBP, and PFS, we use the same SVM classifier. We use an SVM classifier with RBF kernel. So they are equivalent in the classification process as the FCNSV. So the difference here was really the feature extraction part. And here for the CRC dataset, it was also here. The dataset is a little bit. It's the 8th class configuration. So we have here that all the other feature extractors have a little bit of problem to obtain to classify the 8 classes, and we here obtain a huge distance from them. Here is a curiosity that we obtained with our multi-class format. We have here a representation that shows the accuracy, and for each class. So we have here for the back we have 4 classes. For the break-his we have 8 classes. For CRC 8 classes. And we can see here that for each sub-problem, basically here in the back and CRC, they are balanced data sets. So here, even being balanced data sets, in this case, for example, for class 0, we are comparing 600 images from one class to 7 times 600 images. So here we have a very imbalanced scenario, and we were able to obtain, and this accuracy here, it's a balanced accuracy. So we were able to obtain good accuracy with balanced accuracy results, even in imbalanced scenarios. Here in break-his, it's much worse because, for example, in this scenario here, we have a very small class that are compared to the sum of all other classes. So it's very imbalanced. And we were even able to achieve here in all the executions around 0.6% of accuracy. So this showed us, we are not expecting that, but this showed us, and we are very happy with that, that our work can work better with imbalanced data sets. So as conclusion and contributions of our work, we proposed a method that can train models with small texture data sets. So our model, it's kind of easy to train with small data sets and produce better results to the equivalent methods. We haven't tried with bigger methods because it would be kind of unfair, but we plan in the future to explore more this kind of comparison and try to optimize our methods. Here we have a very important aspect that we have a reduced computational cost for small texture data sets. We have a backpropagation that uses that, as I talked about the loss functions. In most of the cases, we only uses the first part of our loss function. We were not. It was not needed to use the misclassified instance part and the correct classified instance part. Only using the support vector part, the support vectors with their anchors, was able to produce very good results. So the other parts, they are like a complementary if we face a complicated data set that need a more separation and everything. So we do not use all images to train. We are already using a small data set, and even then we are not using all the instances to train the weights of our FCN. So we have a backpropagation with less instances than CNN, a conventional CNN, because we don't use all the instances. We only select the best ones. And we have here a very fast convergence if we compare to the CNNs, because the SVM was very capable to separate the classes. The large margin classifier was very competent to separate the classes, and we don't have to train all the network. We train only the FCN part, and we only solve the Lagrangian multipliers with SMO. That it's the best solution for that kind of features that are producing that step. So we are working together. We are working close the feature structure and the classifier. So when they are working together, we were able to obtain this fast convergence here. So we have less cost. The SVM part here was also calculated, great part of them in the GPU. So it's kind of fast. The representation that we created with the SVM, with the FCN, it can be adapted with few steps, with few epochs to each data set to highlight the textures from each data set. So it's very important it can adapt to the problems easily. Also, it can perform well on imbalanced data sets. This was a very good, because this was like the first step of research here, and in the past, that we are working basically with the break-his data set, that is imbalanced data set, and we always faced problems with imbalanced scenario that we face in this data set. So we have this as a plus in our proposal. So this is it. So I'm open to questions now.
Right. Thank you, Jonathan, for the great presentation. So are there any questions?
Yes. Hello, everyone. Can I ask one question?
Okay.
Do you hear me?
I can
Wait.
hear you.
Yes, we hear you.
Okay, I will put my video on. Hello, everyone. Bonjour tout le monde. I am Abdul Hadid from Finland, from France, from wherever you want. So, first of all, thank you very much. Do you hear me? Yeah.
Yeah, I can hear you.
We hear
Yeah.
you.
Thank yeah. Thank you, Jonathan, for the nice presentation. I do like to hear or to see very simple method which works very well. I'm not very fan of deep learning or CNN or something like that. So I am very happy to see some methods which work very well. And so I have two small questions. First one, are you saying, are you trying to prove that CNN is not working with small data or not? Is this the final message that you want to pass, that CNN is not good for if you don't have a lot of data?
Actually, uh, I was not saying that it does not work with small data, because we have a student, for example, our friend Sapra is working with data augmentation, and he's working with histopathological images and small data sets. But he's working with data augmentation, so he's trying to improve the data augmentation to work better with CNN. So they work well with small data sets, but we have to use a lot of tricks to enlarge the data to make them work better. But we can use also the pre-trained networks and everything.
Yeah, because people say that if you have small database, people are using data augmentation, transfer learning, whatever to augment. So, okay, that's fine. My second question and last one is, what happened if there is some wrong labeling in your data? If some super vectors are wrongly labeled, error in the labeling because your method is supervised, you are assumed that the labeling is good. What happened if labeling is incorrect?
Yes, we haven't like thought about that yet, but we are trying now, as we thought, we are trying now to test our model through some robustness tests with adversarial attacks. So by now we are not trying. We are in the middle of this development. So we can even try the robustness of the model using adversarial models in attacking the poisoning our data set. You gave us a very good idea. So I can try this. It's a very good idea to poison the data set.
Thank you very much. Thank you, bravo. Yeah,
thank you.
That's fine. Thank you.
Thank you for the question.
Any other questions for Jonathan?
Yeah, I have a small one. Okay, go ahead, Alessio. Okay, I'll go ahead then. Hi, Jonathan. It's been a while. So I have just one simple question. What is the motivation of comparing and training doing the representation learning from scratch for small data set?
Yes.
Instead of using transfer learning.
Yes, I'm not using transfer learning. The idea here is it's from scratch because I was using like my model. I was not using like a big other network, for example. I was not using a pre-trained ResNet or a predefined model. So this is basically the idea, because I am not fixed with one architecture. I can create any kind of architecture and train it from scratch easily. So this is basically, I don't know if that is my answer.
Okay, thanks.
Hi, Jonathan.
Hi.
Hi, Professor Christian.
Hi, Professor Brito.
Thank you very much for the invitation. I have a question for you, Jonathan. In fact, thank you very much for your presentation. Yes, you have a very nice work, bright ideas. And one question that I think most of people would like to know is that do you plan to test your model for regular images, or not for texture image, but images where you have a difference on shapes and colors. Have you evaluated your model on that?
No, actually, we haven't planned this, because what we plan is to use small data sets. So first of all, it's a small data set. And for example, object, they are, our model, it's designed to produce a small feature vector. And when we try to recognize, for example, objects, faces, and other stuff, we are we need to merge the texture representations with shape, with spatial representation that generates that big feature vectors at the end of the FCNs, and that goes to the FCs and everything, that like very what can I say, sparse representation that goes related to space and everything. And our proposal is to produce simple features, small. For example, this data here that we obtained comparing with the CNNs, we used a very small feature vector with 16 elements, only 16 attributes. So in this case, we were not able to represent very complex information. And these are the idea of the CNN. So we are not competing with them. So
yeah, understood. Nice. Last question. When I read about your loss function that you propose, you have 3 parts there. But when I tried to understood, I understood that the last 2 parts are not so important in the process, as you told to us. Huh?
Yeah.
But one point, they are not important because they are correlated with the first one, or they are complementary, because there is a little difference in if they are correlated, you can focus on the first part and forget the last 2. But if they are complementary, you can for some data sets have some contribution. What are you feeling about that?
Yeah, the point is that, for example, the two first parts, the SV parts and the misclassified parts, they are very correlated, because when we try to optimize, when we optimize the FCN to move the support vectors in the right direction, all the weights from the FCN are updated, and they try to move all the instances in the next epoch. All instances, of course, will move in the right direction. So the misclassified instances probably will move with the support vectors, because they are close to support vectors. So they are going. They have a very big probability to move to the right direction. So this is for the second part. And for the third part, they are important in some data sets that when we try to optimize to make the things closer, they are too packed, and we need some things, so that I call it SH close, because I call it shape. I do like a shape in the data set. So I activate it, for example, at every 4 epochs. Then I do like a shape in the data set that I spread that it's the opposite of the other 2. So I spread a little bit the data set, and then try to compact again, then spread and try to compact again. So it's important in some data sets.
Okay, thank you very much. If I understood, if you can save a lot of time computing the weights in the training process too, huh? Because when you do the back propagation, instead of we have plenty of weights, like you have in CNN, you have a few, because you just take into account the support vectors. Is that right?
The weights are reduced because we only use FCNs. So we don't have the fully connected layers that are produce a lot of weights to train. But what we have, it's less instances to calculate the loss function in the back propagation. So it's
Understood.
much better. And I already, it's not like a very scientific method, but I measured the time to calculate everything. And for example, we have for the back propagation, we have like 8 seconds to calculate 8 milliseconds to calculate the back propagation in our proposal, and in a CNN, due to the using all the instances, all training instances, and the FC layers, we have like 17 milliseconds. So it's very different.
Thank you very much. Thank you, Professor Christian. Thank you, Alessandro, and good afternoon for everyone. Bye-bye.
Thank you.
Thanks. We might have time for one last quick question. I think, Alessandro, you might have a question or a comment.
Yes, sure. Are you hearing me?
Yeah.
Yeah, we hear you.
Okay. Okay, thank you. So thank you for the presentation, Jonathan. It was very nice. I think it's a good idea. You have a good stuff in your hands, but you need to develop it a little bit more. And thank you for Leo for posing the question. I have exactly the same question. I think one of the points is you must compare your approach with pre-trained networks, because the question is, why am I going to use your method instead of using a pre-trained network, even if it's a big network? I don't need to train the network. Maybe I just need to fine-tune the fully connected layer or layers. And in this case, how your method will compare to that? So I think this is the missing part. You cannot. I think you cannot just say, okay, I'll just compare with small networks. I think this is the part that you must work as soon as possible.
Maybe
if you compare if you have good results or similar results, I think it will convince everybody that your method really works.
Yeah, actually, what makes me not compare with the pre-trained model, it's because I came from my previous works. I worked with break his data set, and I have a work. We have a work published with using pre-trained networks with this model. Like we used Inception that we figured that was a good model, and we have an Inception producing like I think it was 1024 feature vector. It's a big feature vector that we use it to extract the data and use an SVM to classify the data, because then we don't have to train a lot of stuff. So we have just the SVM classifier using the SVM pre-trained, the CNN pre-trained, like the Inception, to classify. And we have like few, I will not say problems, but we have some questions with that, because we produced a lot of features. It's a huge feature vector that does not that it's kind of heavy to the SVM, and our results here are better than only using this network as features vector. The results that I know because of my past works. So maybe it's good to recreate that simple results now, just to show using the pre-trained network as a feature structure and compare the.
Okay, so you mean that, for example, for you can, if understood well, your argument, you're basically saying that, okay, I'm working with simple problems, so I don't need a complex representation like those produced by the pre-trained CNNs.
Yeah.
Okay. Good. Thank you. That's all.
So, questions?
So, Christian, no other questions?
Sorry, guys, I somebody knocked on my door. So let's give a big welcome to Jonathan for the presentation. Thank you, Jonathan. And our next seminar will be in 2 weeks, October 28th, on Thursday at noon. So have a great day, everyone, and see you soon.
Thank you very much.
Bye.
Thank you.